Every second of every day, digital infrastructure is under a relentless, invisible siege. Malicious actors constantly probe networks, looking for weak locks to exploit. These probes are the vanguard of a cyber attack, a deliberate attempt to gain unauthorized access to a system, steal data, or trigger a malicious outcome. Some of these attacks are entirely passive. An attacker might quietly intercept communication between two parties, like a man-in-the-middle attack. They don't change the data. They simply monitor the traffic and silently siphon off sensitive information. Active attacks, on the other hand, are aggressive. The adversary forces their way in to encrypt, modify, or completely destroy data. They inject malicious software, like ransomware and Trojans, or flood the system with traffic in a denial-of-service attack until the servers collapse under the weight. To survive this continuous barrage of silent theft and overt destruction, a system has to establish a hardened perimeter. And that starts with knowing exactly who is knocking at the door. Authentication acts as the digital front door. It is the mandatory process of verifying that a user or system is exactly who they claim to be before granting access. Relying on single-factor authentication, typically just a username and password, leaves a system highly vulnerable. If an attacker cracks the password using brute force, dictionary algorithms, or a simple phishing email, the entire perimeter falls. This illustrates how multi-factor authentication solves this vulnerability. The central account hub requires 3 interlocking elements locking into place: something you know, a password; something you have, a token; and something you are, a biometric fingerprint. Stacking these factors increases mathematical difficulty exponentially. But a strong lock only protects the entrance. Once an identity is verified, whether it belongs to a legitimate employee or an attacker with stolen credentials, that user is inside the network. If they are allowed to roam freely, they can still cause catastrophic damage. This is where protection models take over. These are the formal, hard-coded frameworks that dictate exactly how subjects, like users and processes, are allowed to interact with objects, like files and memory, once they are inside the perimeter. These models enforce specific pillars of security. The Bell-LaPadula model, for example, is engineered entirely to enforce confidentiality. It ensures that sensitive information stays completely secret. We can see Bell-LaPadula in action on this 3-tiered pyramid. The model enforces a strict no-read-up rule. When a user on the bottom tier attempts to access a classified file on the top tier, the upward connection is instantly rejected. You cannot read data at a higher clearance level than your own. The model also enforces a no-write-down rule. If a top-secret user tries to move a classified file to a lower public folder, the system intercepts and dissolves the data packet. This mathematically prevents someone with high clearance from accidentally or maliciously leaking secrets to a lower tier. Bell-LaPadula perfectly prevents secrets from leaking out. However, it does absolutely nothing to verify the accuracy, purity, or safety of the data coming in. To protect the integrity of the data itself, systems use the BIBA model. BIBA is the exact structural reverse of Bell-LaPadula. Instead of focusing on secrecy, it focuses entirely on preventing corruption. Looking at this vertical flowchart, we see BIBA's no-read-down rule. If a pristine, high-level system attempts to pull unverified, unstable data from a lower tier, it activates a shield to block the intake. Secure systems must never rely on untrusted data. BIBA also enforces a no-write-up rule. When a low-level or outside user tries to push data upward to overwrite crucial high-level code, the barrier repels it. By blocking untrusted inputs and restricting low-level edits, BIBA builds a mathematical cage. It dictates exactly how data is allowed to move, ensuring vital systems remain uncorrupted. The modern cyber arms race exists because attackers specifically map out the spaces between these rules. They study the architecture, looking for the one gap in the logic. Phishing campaigns and brute force password attacks are straightforward attempts to bypass the authentication perimeter entirely, tricking the system into granting authorized entry. Active attacks, like destructive malware injections, are deliberate efforts to fracture the integrity rules guarded by the BIBA model, attempting to overwrite clean code with corrupted instructions. And passive attacks, silent monitoring, and data interception are sophisticated operations designed to circumvent the strict confidentiality barriers established by Bell LaPadula. Information security relies on an interlocking architecture of identity verification and strict behavioral laws, constantly adapting to neutralize an ever-evolving threat landscape.